the CH425 as well as CH812 post-mid semester session. Okay. So someone can tell me what is being taught so far. My understanding is that up to hydrogen atom, things have been covered. Yeah, Anish,
Yes,
tell
sir.
us. Yes.
Postulates of quantum mechanics, particle in 1D and 3D box, and tunneling problems, a few tunneling problems, and finally hydrogen atom and angular momentum.
Okay. Now, last year I taught this class along with Professor Rahul Maitra, but last year I had taken the first portion of the course. Okay. So I'm just sharing this. If you go to this link, you will find the class notes and the video lectures of this course. Also other courses, but this particular course, CH425, and we're using same set of lectures for CH812. So Anish, you can go there, click, and I'll show you how to do it. This. Can you see the screen?
Yes, sir.
Yes, sir.
So if you go there, you will see the 812 and 425. There's one called link to video lectures. And if you go down, you will see that this is half semester notes. So these are, so if you click there, it will download all the PDF file of the handwritten notes. And these are the same notes in parts, okay? And if you click there, link to video lectures, you'll go to a drive and you can see all the lectures here. Can you see? All are listed.
Yes, sir.
Yes, sir.
And I had asked you to look into this. Lecture number 15. This is session 15, this one, for today's class. So how many of you had a chance to go through or at least glance through?
Yes, sir.
Yes, sir. Not too many yes, sir.
Yes, sir.
Yes, sir.
Okay.
Yes, sir.
Good. So because I plan to do this, what is known as angular momentum, which is a very important topic in quantum chemistry and quantum mechanics. What happens if you are in chemistry, you are not taught classical mechanics properly. So it is always good to have bit of background in classical mechanics, and then only you should move to quantum mechanics. You start learning quantum mechanics, but that is not the case. Anyways, we'll do. But before we do that, actually, let me stop sharing, and you can introduce yourselves. First of all, let us start with CH812. Who are there? CH812. Who are there in the class? Are there people for CH812?
Yes, sir.
Okay.
Yes, sir.
Okay, so maybe you can introduce
sir.
yourself. You can switch on your videos one by one. People who are taking CH812, and introduce yourself. Shaivi, you want to introduce yourself?
Yes, sir. Hello,
Yes.
sir.
Hello.
This is Chevy. I have joined your PhD in the lab of Professor Naresh Patwari.
Okay, so where did you do your master's?
I've done my master's from IIT Guwahati
Okay. Okay.
and my bachelor's from Miranda House.
Okay, but you are doing it from home, no? Like.
Yes.
Okay. Good. Next one. I don't know who wants to introduce.
Hello, sir.
Yeah.
This is Mansi, and I have joined Dr. Arindam Chaudhary's lab.
Okay.
And I have done my MSc from Himvati Gadwal University.
Okay. So you're also joining from home. Yeah. So you guys are at home. Okay. Good.
Yes.
Who is next?
Hello, sir.
Yes.
Tovik here. I am from West Bengal. I have done masters from Jadavpur University, and
Okay.
here I am joining to Professor Isita Sengupta's lab.
Okay. Ovik Ghoshal. Okay, good.
Yes, sir.
Who else?
Hello, sir.
Hmm.
Sonaldeep here, and
Yes.
I'll be joining Professor Rahul Maitra's lab, and I've done my MSc from Calcutta University and PSc from Calcutta University as well.
Okay. Good.
Oh,
Thank you, Sonaldeep.
thank you.
Who? Yes. Next, Dibbendu.
Yes, sir. Good morning, sir.
Yes.
Here I have joined Dr. Rahul Mohitra's lab, and I have completed my masters from Calcutta University as well.
Okay. Good. Anyone else? From 812? Okay, if there is no one from 812, okay, Rajdeep. Yeah.
Hello, sir. I am Rajdeep, and I did my master's from IIT Bombay, and I am joined Dr. Rajaraman's lab for my
Okay.
PhD.
Okay. Who else? Anyone else? No one? Okay, then we'll move to CH425. CH425. Maybe the MS students can introduce MSc students 2 year. Can introduce themselves one by one.
Yeah. Good morning, sir. I am Tushant, and I'm here doing masters, and I have done my graduations from Kirodimal College, University of Delhi.
Okay. Okay. So it is difficult to no, Tishan, thank you. So if everybody introduces, it will take time. Maybe few more from MSc, then we'll move to BS.
Hello, sir. I'm Anika.
Okay.
I'm also from Kirodimal College, University of Delhi.
Okay, MSc.
Yes.
Thank you. Okay, so one more from MSc maybe. Who wants to come? Yes, Ayan.
Hello, sir. I am Ayan. I am from West Bengal. I am joined MSc course here, and I did my graduation from Ramakrishna Mission Vidya Mandira, University of Calcutta.
Okay, so maybe one more from MSc.
So good morning, sir. My name is Jaideep Mandal. I am from West Bengal. I did my graduation from Krishnath College, Bahrampur, and I joined the MSc course.
Okay, so few from BS they want to introduce who are taking 4 to 5. Anyone?
Hello, sir. This is Vatsal.
Yeah.
I'm a third year BS student. And, yeah.
Louder, little louder. Where are you now? Right now?
At home. It's
Yeah.
Bareilly, UP.
No, you have blackboard, whiteboard. Okay, good. And who else wants to introduce? Anish, you want to introduce yourself? Because I know him. He has left the meeting. Anyway, who else? Anyone from BS?
Yeah, sir. Morning, sir. I'm Chinmay.
Yes.
I'm third year right now. Taken 4 to 5.
Okay. Yeah. Anish?
Sorry, I got disconnected. Good morning. This
Yeah.
is Anish, third year BS student
Good
from
morning.
Kolkata.
Okay, good. So you're at home, still at home.
Yes, still at home.
So when you guys are coming back to IIT, or you will graduate without seeing the campus?
No, we have seen the campus.
No, you have seen the campus, but I don't know.
Hopefully by the end of this semester,
Hopefully.
most of third year students will be back.
Okay, so maybe one or two girls from BS, they want to introduce. Anyone? So no girl from BS this year? Maybe nobody wants to introduce. Okay, so maybe I can call people by name, one or two. I don't even know there, but there are people I can see. See, Elisha Chakraborty, are you from BS or MSc? I can see the name.
No, sir, I'm from MSc.
MSc, okay. Where did you do your bachelor's?
Sir, Jadavpur University.
Okay, good. Hanshika Arya, are you there?
Yes, sir.
You're
Good
BS or
morning,
MSc?
sir. Sir, MSc student.
MSc, okay.
Yes, sir.
And Saizal Mina? Saizal?
Yes, sir. I'm Sejal. I'm from Rajasthan. And currently I'm pursuing graduation from MLB Government College. And I'm here for MSc course.
Okay, good, good. Anyway, I don't know who are from BS. Anish, can you help me? Anish?
Yeah, I am Deepika, sir.
You're from
And
BS? Oh, good, good.
yeah,
Yeah, tell me.
I'm from BS.
Good. Very good. Anyway, so far how the course is going, tell me. All of you can, like one by one, you can tell me. They will start. By the way, you know my name. My name is Rajarshi. Okay, I'm a faculty member in chemistry department, IIT Bombay. And my area of research is actually statistical mechanics, theoretical chemistry, actually interface between chemistry and physics. Yeah. So, yes, anybody wants to comment on the course? How it is going so far? I hope you're enjoying the course.
Yeah, it was good. The connection between physics and chemistry.
Yes.
Yeah,
Because
quantum.
some of you had taken quantum physics course.
Yeah,
And those
in
are
first year.
I think those are more advanced and mathematical maybe. Yeah. Anyway,
In
so
first year.
you have been taught bracket notation
Yes, sir.
in this course. Has it been
Yeah,
taught?
yeah, yeah. Yes, sir.
But
Okay,
it has
so
not
linear.
been used very extensively. Mostly we've been using integral notation.
Yes, sir. There's little bit of.
Okay. Well, let's see how it goes. I can use integral, it doesn't matter. But anyways, we'll start now. It's coming back to angular momentum. So how many of you had gone through this note on angular momentum? Tell me.
Yes, sir.
Anish, you have gone through.
Sir, I have,
So, yeah, who is this? Yeah, tell me.
yeah, sir, I have gone through the video, not the note actually.
Okay, yeah, video you have gone through, no? Yeah, that's even better. That is even better. So, could you follow the video, Savia?
Yes, sir.
Okay, you are in which course? CH 812, 425 MSc. Okay. Yeah, so I'll just revive or just refresh your memory if you have gone through. So let us start presenting. I think you can see the PDF. I hope you can. Can you see the
Yes.
PDF? This is good?
Yes, sir.
Yes, sir.
Yeah. Okay. So we'll start from here because you have been taught hydrogen atom problem. So hydrogen atom problem is one of the problems in quantum mechanics, non-relativistic quantum mechanics, which can be solved exactly, analytically, without using a computer. You know that, all of you. At least you say yes, huh? Some of you. When I present, I can't see your names or faces because I am just looking at the PDF. So the Hamiltonian looks something like this. This everybody knows, no? This is not a very difficult. This is the electronic part of. So this is X is actually what is known as this relative separation between the nucleus and the electron, isn't it? R. It has three components: X, Y, and Z. So you can write down the Hamiltonian. It is given by this. How many of you know? Or you can, if I ask you, you'll be able to write this Hamiltonian. No, this has nothing to remember. This is in Cartesian coordinates.
Yes, sir.
Very simple.
Yes,
H
sir.
cross square by twice mu. Mu is the reduced mass. Then this grad square operator. Then minus 1 over r. And minus 1 over r is the electron nucleus attraction, isn't it? And if you want to be more precise, then it is actually E square by 4 pi epsilon 0, isn't it? The prefactor. Fine. So
Yes,
what
sir.
is r? R is root over x square plus y square plus z square. Okay. Now this hydrogen atom problem has something known as spherical symmetry. You know that. I think it is discussed. So basically the potential is such, it has spherical symmetry because it is, if you go from the center radially outward, the potential energy changes. But it doesn't depend on any angle, isn't it? Any direction you can go from the origin, radially outward. The potential energy depends only on the value of r, not on the value of theta or phi, isn't it?
Yes, sir.
Yes,
We have a spherical symmetry in that problem. Actually, this is an example of, in classical mechanics, what is known as central force problem. If you have learned a bit of classical mechanics, you will see. So this problem has what is known as spherical symmetry. Is this clear?
Yes, sir.
Why? Because the potential is such that if so for example, the nucleus and electron attraction does not depend on whether the electron is here or here or here. As long as they are at equal distance from the nucleus, the interaction energy is the same, isn't it? Of course, I'm talking about, I'm using the language of particles, like as if electron is a particle, nucleus is a particle, like this. Anyway, I'm doing quantum mechanics. Anyway, now this also ensures that your Hamiltonian will commute with some other operator, which you'll see. This happens with problems where you have spherical symmetry. Okay, that I'll see later. But if I ask you a simple question that, okay, your Hamiltonian and linear momentum operator for hydrogen atom, do they commute or they don't commute? Tell me. It is written in the PDF, but can anyone tell me whether they commute or not? And if
No,
they
sir.
do,
If it's
yeah.
linear momentum, then it doesn't commute, but angular momentum, it commutes.
Angular momentum will come later, but linear momentum, it does not commute, isn't it?
Yes, yes.
So what does it mean?
It will not
They cannot be
follow.
calculated simultaneously.
Yeah, it basically means that we cannot simultaneously measure the energy, which is the eigenvalue of Hamiltonian, and the linear momentum, which is the eigenvalue of linear momentum operator, isn't it? So there will be some uncertainty associated with energy and momentum, isn't it? You cannot simultaneously measure them without uncertainty, isn't it? So in other words, momentum has no precise value. It will have some uncertainty. Is this clear? So this happens when you have two operators, A and B, they don't commute. This is a problem. And this is actually not the problem, this is the outcome, the consequence of two operators not commuting. Is this clear? This has been taught, I'm sure.
Yes, sir.
Yes, sir.
Yes. So, but why they don't commute mathematically? If you look into this expression, you see that the first portion has nothing, no problem, because px is minus h cross del x, some constant time del x. So this part will commute, isn't it? If I write h px minus px h, this part will commute. The problem is with this part, isn't it? Is this clear?
Yes, sir.
So if I go to free particle, you have the, for a free particle, you have a Hamiltonian something like this, no? Only this part, because you have only kinetic energy for free particle, isn't it? So for free particle, I don't have this problem. They will commute h and px. What do you think? Will they commute or not?
Sir. Yes, sir.
Yes, sir. It will commute.
So basically, you will see that for free particle, you will have a common eigenfunction for h and px, isn't it?
Yes, sir.
Yes.
Yes.
So h and px. Now, what is that common eigenfunction? Can anyone tell me for free particle?
In the plane wave solution.
Minus h cross square by 2m.
It is just like plane wave, exponential of ikx kind of solution, isn't it? Because if you operate ih cross minus ih cross del x, kh cross will come down. That will be the value of momentum, isn't it? Are you getting this? Exponential of ikx. And if I operate this operator on exponential of ikx, I'll get kh cross into exponential of ikx. So kh cross is going to be the value of the linear momentum, isn't it? But at the same time, if I operate this, say del square del x square, in I'm considering a simpler case in one dimension, then it will also give you something like h cross square by k square, kind of by twice mu kind of prefactor, then the eigenfunction back. So this is also going to be an eigenfunction for the Hamiltonian, isn't it? You can go and check yourself.
Yes, sir.
It is very simple. I'll do that later, but it's very simple. Okay. So one thing is that if you two operators commute, they will have one common set of eigenfunction. You know that?
Yes, sir. Yes, sir.
Now I go back. Now I again write down the Hamiltonian of hydrogen atom, but in spherical polar coordinate. It will look something like this. What I've written here. Okay. Don't get scared. I don't expect you to remember this expression. I expect you to remember this, because this you can write from the concept, isn't it? You know. This one is a little difficult to remember. If you can remember, that will be fantastic. Okay, so it's the same Hamiltonian but written in terms of spherical polar coordinate. You remember these things, r, theta, and phi?
Yes, sir.
Yes, sir.
I am not drawing it here. Okay. So after today's class, please go through my lecture number 15 recorded last year. It calls session 15 or something. Yeah. So your Hamiltonian has something like radial part. Can you see this is a radial part? It depends only on r. This is a constant. And then you have this part, which is a function of theta and phi. No r dependence. Okay. So I can call this part, say I'm calling it A, operator A, this part, and divided by r square, because they have 1 over r square factor. So my Hamiltonian is something like a part which is a radial function of r only, plus A, which is which depends on r, theta and phi, divided by r square minus e square by r. Okay. So now, can you tell me whether this Hamiltonian will commute with A, this operator, just by looking at it? Can anyone tell me whether it will commute or not? Anyone? Anyone
Yes,
from
sir.
812? Anyone from 812? Anyone from 812 wants to comment on this? Shaivi, you want to comment?
So,
You can you tell me whether this Hamiltonian will commute with this operator A. This I am calling A. This part.
I couldn't follow the last few parts. I mean, I'm not able to see the screen.
Now it should be able to see. It is projected, no? Can others see?
Yes, sir. We can
Yes,
see.
sir. It's visible.
Yeah, everyone can see. You should be able to see that as well.
So maybe I'll rejoin because there's some connection.
Okay. So yeah, okay. Anyone else has a comment whether it will commute or not? It will commute or not? It will commute, isn't it?
Yes, sir, it commutes.
Yeah, because
R part has no explicit theta dependence and theta part has no explicit R dependence.
This is R dependence, so it is theta and phi. This will commute with this part. Again, this has R dependence. It will commute with this part, and this also has A itself. So A itself will commute with itself, isn't it? So the operator H will commute with this this operator A. What does it mean? Basically means that if I can connect this operator to some physical observable, then this physical observable along with energy can be simultaneously measured without uncertainty. Is this clear? Is it clear, the statement? If I can relate this operator to a physical observable, then that physical observable and the total energy, that these two can be measured simultaneously without uncertainty, since Hamiltonian H and operator A, they commute. Is this clear, this statement?
Yes, sir.
Should be easy to follow, isn't it? Because if two operators commute, then the corresponding eigenvalue, corresponding physical observable can be measured simultaneously without uncertainty, isn't it? Like in free particle, H and Px commute. So simultaneously you can measure energy and momentum, linear momentum. So here simultaneously you should be able to measure energy, which is the eigenvalue of Hamiltonian H, and something else, which is the eigenvalue of this operator A. Okay? I hope you are following. Now, can anyone tell me what is this operator A? Or what, it is related to some operator. What is that operator?
Total angular momentum.
Angular momentum.
Yes, total angular momentum. We'll see that. Yes, we'll see that later. Huh?
L square operator.
Yeah. So now we go back to a little bit of classical mechanics. So let us, if you have, you know that in circular path, the angular momentum is given by MBR. But the general definition of angular momentum is given here, isn't it? Angular momentum L is a cross product between R and P. What is R? R is this radial vector. So if this is your nucleus, the electron, then this is the R vector, and the electron has this momentum vector P. So the cross product between R and P will give you angular momentum. So, for example, this is your nucleus. Can you see me? This is your nucleus. This is your electron. Can you see me?
Yes, sir.
Yeah. So nucleus, electron. This vector is R going outward, and this electron is. So I'm giving you a very old picture: circular motion of electron around, or orbital motion of electron around nucleus. And there's a momentum vector like this, going like this, P, linear momentum. So the cross product of these two, you know, from classical physics, it will be like this. You know this. This is the direction of angular momentum.
Sir, can you please raise your hand a little upward?
Yeah. Can you see this? This is angular momentum going to be. This is linear momentum. This is radial direction vector. And this is angular momentum is going to be, isn't it? It is perpendicular to that plane, the direction. Is this clear?
Yes, sir. Yes, sir.
Yeah, so this is a cross product. Obvious that the angular momentum is going to be this one. My thumb is going to be a vector which has some direction as well as some magnitude. Okay, And you know how to calculate the cross product of two vectors, A cross B? You have to write the components of the vector. R has three components, X, Y, Z. Linear moment has three components, Px, Py, Bz. Of course, this I, J, K. This I is not imaginary I. This is the unit vector along X. I cap, J cap, K cap. Okay. And then you write L as this determinant. You know this I, J, K, X, Y, Z, Px, Py, Pz. How many of you know this? I, J, K, X, Y, Z, Px, Py, Pz.
Yes, sir. From
This is from your school days.
Yes.
School days, yes. So now if an L is a vector, it will also have three components, Lx, Ly, and Lz. So I can also write it as Lx plus Ly plus Lz. Of course, I cap, J cap, K cap. This is fine. Three components. And these are Px, Py, Pz. These are the these are defined here. So L is going to be what? Now Lx. Now if I expand this, you know, L is going to be I cap times ypz minus zpy. Can you see that? Ypz minus zpy. Ypz minus zpy. I cap. And J is going to be again zpx minus xpz. Ly. Similarly, Lz xpy minus ypx. I am just expanding the determinant. Is this clear? This is class 11 math.
Yes, sir.
Physics. So I can interpret these as Lx, Ly, and Lz. Lx, Ly, and Lz. This is fine. And there is a cyclic rule here, x, y, z. You see? X, then y, then z. This is always like the x, y, y. You can see x, y, z, x like this. Y, z like this. Okay? So Lx is ypz minus zpy. If I take this. If I substitute the value, the expression for pz and py, I have minus ih cross common. I take it outside. It will be y del del z minus z del del y, which is Lx. Similarly, I can have expressions for Ly and Lz. This is fine. These are expressed in terms of Cartesian coordinates x, y, and z. Is this clear to all of you? This is very, very simple thing to do.
Yes, sir. It's fine.
Yes, sir. Fine.
Yes, sir. Clear.
Yes, sir.
Yes. So I don't think we should spend time on this. Now, obviously, this is a vector. So if I take a square of this, it will be Lx square plus Ly square plus Lz square. This is the total. This is the square of the total angular momentum vector. Square of the total angular momentum vector. Huh? And you can check that this is true. Now, let us try to see what happens if I try to construct the commutator of Lx and Ly. Lx and Ly. Okay, so let us see. Now Lx comma Ly, how do you do this? You can see my video. The video has the total derivation, essentially the same PDF I'm using here. So you have a little lengthy derivation, but you can show that if you construct the commutator between Lx and Ly, obviously it is Lx Ly minus Ly Lx, isn't it? So it will have minus IH cross. This is IH cross. The cross has not, somehow it is not appeared. It has not appeared here, cross. This minus IH cross whole square, isn't it? This factor. This will come out. And then you'll have this one is what? This is like Lx Ly minus Ly Lx. And you're operating this on a function which is a function of x, y, z, f. And if you do the algebra, you will see that this is equal to IH cross Lz. So they don't commute. Lx Ly equals to IH cross Lz. This is like a cyclic rule. X, y, yx, that gives you Lz with IH cross. Has it been taught earlier in this course? This angular momentum commutation relations? Hello?
This result we used.
Used for what?
Sir, during hydrogen atom, reading the hydrogen atom.
Okay, but did you derive this?
Yes, sir. I can derive.
Now you can derive, but has it been derived in the class?
No, sir. No.
Okay, but you can see my class notes and the video and you can see how to derive, but I can tell you. So I can give you a hint. When you multiply this with this, what you get? Y del del z, z del del x, and then f. And if I expand this, what I'm going to get? Y. Now this is like del del z operating on z, and this the whole thing. The first term will be y. Del del z operating on z gives you 1. So y times 1, and then del f del x plus y. Now this time z will come out, and del del z will operate it on this. It will be yz plus del 2f del z del x. Is this clear? What I'm doing here?
Yes, sir.
Yes, sir.
It is very, very simple, and you will see that you will get many such terms, and some of the terms will cancel each other, and eventually you will get this Lx Ly equals to IH cross Lz. Eventually you will get this. Okay? So you can go and check yourself.
Sir,
Yes.
second term, please explain.
Sir, in this order of differential will affect it or not? Because then that term that we are cancelling is
No, it
order
doesn't
of-
matter. Does not matter. Does not matter. Okay. Yeah, the second term is very simple, no? Because y del del z operating on z and del f del x.
Sir, not.
What?
Sir, here y del del z x del f del z.
No, you y times.
I'm talking about second term, sir. Y del z x del f del z.
This one.
Yes, sir. Yes, sir.
Yeah, because because if I operate del del z on x, it will be 0. First time will be 0.
Sir, how it is?
Because x has nothing to do with z. How can you differentiate x with respect to z?
Here x is constant.
Not a constant, but x has nothing to do with z. So how can I do del x del z? It will be 0.
Okay, sir.
X has no z component.
Okay.
It will be 0. And the second term will be x will come out minus yx, and this will operate on this. This will give you del 2f del z square.
Okay.
Okay, so just do yourself. This is very simple math. This is like school math, I would say. People who had class 11, 12 calculus can do this. Okay, so these are the relations. If you do yourself, you'll see that these are the relations. And you can also check that L square and Lz, if you try to construct the commutator, it will be 0. Yes, someone has a question.
Yes, sir, I'm asking one thing. That's if we write this Lx as ypz minus zpy in this way, and then just split the commutator as we can write a plus bb, a plus commutator of a plus bb, that can be written as ab plus bb in this way. And then, sir, we'll cancel all the terms like py, we'll get the terms like pxz, pyx, they will cancel, and then I will get a commutator finally that is like xpx, and then I can just evaluate that, and I can also derive the result.
Yes, many ways you can do. I just did it explicitly. You can use commutator relations or anything, any trick you can use.
So that is easy related to.
Yes, but I wanted to show this because I think many people cannot even do this. Someone is asking, no, why it is minus yx del 2f del z square. I wanted to show explicitly that you get this.
Yes, sir.
There you add something, subtract something, and then you take common. I know. Okay, so now, so this L square and Lz, they commute. L square and Lz commute. I had, okay. Yes. So these are the relations. Hamiltonian commutes with L square. Now, what is L square? If you see carefully in Hadamard problem, you'll find the one I had shown you, the A, with the, if I multiply that with minus h cross a square, I'll get what is known as operator for the square of the total angular momentum. Is it clear? You see, this one was appearing. No, this one was appearing here. The Hamiltonian showed you at the very beginning. This one. So if I multiply this one with minus h cross a square, then I get what is known as total angular momentum square operator, L square. Where is that? Yes. Total angular momentum square operator, L square. This is clear? Because I am not doing it detailed because it must have been done in hydrogen atom problem. You can go and check my notes and also my recorded lectures from last year. Okay, now L square will commute with H. We had already shown that. So L square will commute with H in this case. And then as a result, what is going to happen? This, because of these commutation relations, you will have a common set of eigenfunctions, isn't it? Because if two operators commute, they have a common set of eigenfunctions. Is it clear? Yes.
Yes, sir.
And what are these common set of eigenfunctions? Can anyone tell me? So can you give me yes? Can you give me yes? Yes. Somebody says. Okay. Okay. So actually you see your Hamiltonian is like this: kinetic energy due to radial motion plus kinetic energy due to this angular motion, and then in this potential energy, isn't it? This is your Hamiltonian for hydrogen atom, isn't it? This one looks exactly like this. This is like what? This is like L square by twice mu r square. This is, you know, that p square by twice m kind of thing, isn't it? But in terms of angular momentum, this is the kinetic energy due to angular motion. This is kinetic energy due to radial motion. And then this part is potential energy due to interaction between the nucleus and the electron. Clear? Also, LZ has this expression minus IH cross del del phi. You can check yourself. So we go back to hydrogen atom problem. The total wave function is given by what? Radial part plus angular part. What is that angular part called? Spherical harmonics. It depends on theta and phi and depends on two quantum numbers, L and M. So you know how these quantum numbers are coming. That has been discussed. Has it been discussed?
Sir. Yes, sir.
This n element. Actually, you can also see my class notes and video lectures where I had derived all the hydrogen atom, this what is known as this power series thing, and derived all the relations between L, M, and N. Okay. So someone was telling, maybe Anish, that spherical harmonics, they form a common set of eigenfunction. That is true, because if I operate L square on this total wave function, R part will be unaffected by L square. No, it has nothing to do with theta or phi. It will come out. So L square will operate only on the Y part, which is a function of theta and phi. Okay? Is this clear? Is this clear to all of you?
Yes.
Now you remember that what happens. This when L square operates on Y, it gives you L into L plus 1 times H plus S squared times the spherical harmonic back. You know that? So L into L plus 1 into H plus S squared. This is the eigenvalue for the square of the total angular momentum. So if I take a square root of that, that will give you the length or the magnitude of angular momentum, total angular momentum, which is root over L into L plus 1 times H cross. This one you know. This is orbital angular momentum, the value.
Yes, sir. Total angular
And
momentum.
if you recall the hydrogen atom problem, you'll see that you'll have something like this. The way I had derived last year, I think it has been done similarly in this year. You'll have something like this, and this relation was used there as L into L plus 1. Remember, H cross S square, like this. This is the theta part, this is the phi part. For the phi part, you had this equation, and for theta part, you had this equation. Okay, so let us check few things. So let us take this phi part. Phi part has this relation, this expression, you know, exponential of Im phi kind of solution. You remember this? M is the magnetic quantum number.
Yes, sir.
M is the magnetic quantum number. So now when Lz operates on this, Lz is this, it is going to be 1 over 2 I pi is constant. So this will bring down Im, and this I square will cancel, will combine and give you -1. -1 is +1. You'll get mh cross times the function back. So mh cross is the is the eigenvalue. Is the eigenvalue for what? Can anyone tell me what is the mh cross is the eigenvalue for what?
Angular momentum along z component.
Yes, z component. So basically Lz also has this phi m equal to mh cross this. But you remember that Lz Ly and Lz Lx, they don't commute. You cannot know simultaneously with precision Lz and Ly, the values for Lz and Ly. So the idea was like that. So for a given value of L, L equal to 1, for example, you have 3 values of m, 0, 1 and -1. For 0, the length is 0, which is this point. For +1 and -1, okay, the length of this is what? How much? Tell me. L into L plus 1 is 1. Not the length. Length is always 1 into 1, root over 2. Length is always root over 2 times h cross, like this. This is the length. It's not properly drawn. But the projections are different for different m. This is for m plus 1. This is for m minus 1. And this is for m
0.
And this is what orbital is this? Any idea? You remember this orbital? L equal to 1.
P orbital.
P orbital. What are these P orbital?
Pz.
And?
Px, Py.
No. This is the problem.
P plus 1 and P minus 1.
Minus 1. Yes,
so
sir.
it is actually Pz, which is for m equal to 0. And then you have P plus 1 and P minus 1. And Px, Py are not m equal to 1 or m equal to -1, isn't it?
Yes, sir. Linear combinations.
The linear combination in such a way that the expression is not imaginary. Not imaginary, yes. But because physicists, they don't talk about Px, Py. They take just P plus and P minus. These are the solution. But chemists like to see things pictorially. So that's why they want functions which are not imaginary, which are real. So they take a linear combination of P plus and P minus and make Px and Py. Okay? This one you know. This one you know.
Yes, sir.
Sir.
Yes.
Sir, in quantum mechanics, we know that the eigenfunction, the wave functions can be complex.
Yes.
And sir, in this case, we are taking 2p plus 1 and 2p minus 1. They're essentially imaginary. So, sir, why do we not go with these imaginary functions?
You can do it. No problem. No problem at all.
So, is there any bonding consequence?
No, so actually, what happens? Chemists like to explain things in terms of orbitals, and orbitals are constructed in such a way from the solution that they all are real. Chemists don't like imaginary orbital. They want real orbital. And then they use the language of orbitals, the overlap between the orbital, to explain chemical bonding. This is their way to explain things. Okay? But mathematically, this is a solution as well as Px is a solution. Yes. Mathematically, m equal to 1 is a solution as well as Px, the expression for Px is also a solution. The expression for Py is also a solution. Physicists don't go to Px, Py usually. They stop there and they play with, they deal with these solutions, imaginary solutions. They have no problem. But chemists don't like imaginary solutions. They want to see things pictorially and they go to real solutions. Okay, so that they can construct real orbitals, some pictures, and they want to see the overlap between the orbitals, all these things. All the orbitals are nothing but one electronic functions. But to chemists, they want this. They want real functions to be orbital, and they can calculate. Yeah, they can see the overlap between these orbitals and explain things accordingly. So chemists who are doing things. Okay.
Yes, sir. Got it.
So Anish, in your physics course, you had taken a course, Anish and others. So was it discussed? These orbitals were discussed.
Yeah, it was stopped at plus minus 1, I think. 0 plus minus 1.
Yeah, so they did not discuss maybe Px, Py, like going to constructing real functions. They don't do much.
Yeah, no, that was not the focus. No.
Yes. But chemists like it, They go to the real functions and deal with real functions. So this is the overall view of angular momentum. If you want, you can read more about the angular momentum. There's a person called Richard Zehr. He has written a book on orbital momentum. If you can access that book, I don't have the book, but if you can access the book, you can read. But that is not important for this course, but it is always good to read things, good to know things. So you can go ahead and read. And what are the books you're following? I'll now stop presenting for the time being. What are the books you're following?
Zetili.
Zetili is okay. What else?
Griffiths.
Yeah, there is a nice book by Shankar, R. Shankar, on quantum mechanics. A nice book on quantum mechanics by R. Shankar. You can go and read that book. There is a book, like 2 volumes, by Cohen Tanoji, quantum mechanics. Okay, so you can go and read that book as well. And there are books written by chemists like Levine. That is also a nice book. Pillar. You can read those books. But it's always good to read books. Get the language and get flavors from different books. It's always good to read more books. At least you should read 2-3 books. That helps. That helps a lot. And what I plan that in the next class we'll introduce spin. Maybe briefly we'll discuss spin today, but we'll introduce spin in the next class. So has it been taught, spin of an electron?
Not in this course.
Not in this course. So when you do this non-relativistic quantum mechanics, actually what happened that in non-relativistic quantum mechanics, you bring spin as an additional postulate. Okay, there are experiments by Stern-Gerlach. How many of you know the experiment by Stern-Gerlach? Have you heard of Stern-Gerlach experiment? How many of you?
Yes, sir. No, it.
You have not, or you have?
We have.
Yes.
Yes,
So
sir.
can anyone tell me what is? Can anyone describe me the experiment by Stern and Gerlach? It would be nice if someone can explain.
If I remember correctly, silver atoms are ejected and made to pass through an inhomogeneous magnetic field. And then after the pass through the magnetic field, we see their arrival on a screen by some detector, and we see 2 distinct spots, if I'm not wrong. And that is what led physicists to propose that given no orbital angular momentum, even then this kind of motion can be observed, which means that there is another intrinsic property in the electron, and that is what was an experimental demonstration of spin.
Yes. So it was done with an 1s electrons, which has L equal to 0. So no intrinsic, no orbital angular momentum. But even with that, when the electron passes through an inhomogeneous magnetic field, it splits and make 2 spots on the screen. So it basically tells you that there is an inherent, even if you have no orbital angular momentum, even if your L is 0, even if your electron is sitting in s orbital, it has some intrinsic momentum, angular momentum, and that is attributed to what is known as electron spin. But everybody should know it has nothing to do with physical spin. Okay, it is not, electron is not a tiny ball which is moving on its axis, clockwise, anti-clockwise. All these things are wrong representation. These are the concept of spin for electron is totally quantum mechanical. For subatomic particles, when you talk about spins, these are entirely quantum mechanical concepts. Okay, this concept has nothing to do with physical spin. There is no object which is spinning on its axis. Okay, is this clear to all of you? Is this clear to all of you?
Not very much, sir.
What I'm saying that electron has no spin, like electron is not a tiny ball, it is not revolving around its axis. If you know like this is wrong. This is some intrinsic property of the electron that is known as spin. And you will see the algebra. If you do the algebra, it is exactly like the algebra what you do for orbital angular momentum. But it is spin does not mean it is spinning. There is no such called spinning. And spin up, spin down, all these are wrong concepts. There's nothing called spin up, spin down. But we can sometimes we call it spin up, spin down. Okay. The inorganic chemists explain things based on these. These are wrong things. Okay. There is no such thing. Electron spin has nothing to do with physical spin. Anish, this is clear to all of you, I am sure. Anish, are you there or anyone else?
Yes, sir. Yes, sir. Clear to me.
Sonaldeep?
Yes, sir.
So you know this, that electron spin is not a spinning electron.
Yes,
not
sir.
a tiny ball spinning on its axis.
Yes, sir. I know this.
And that is very important.
Sir.
Yes.
Sir, I'm not able to get a picture of what are you trying to say. So, like, how do we imagine spin? Like,
there is no classical analog, so you cannot imagine spin. That's the whole thing.
So, how am I supposed to understand this? Like,
there is no classical analog. This is an extra degree of freedom electron has, which has some rules. It follows some rules. It is quantized, okay, but it has no classical picture. So that's why you cannot come back to classical mechanics and think that electron is a tiny ball spinning on its axis. All these things are wrong.
Then why it is saying that is electron is spin?
It is, we call it spin. We can call it something else. We could have called it something else. It has nothing to do with spinning of an object. Just it is called spin. Historically, it has nothing to do with spin. Electron does not spin on its axis. Electron is not a tiny ball. Electron is a quantum mechanical object, isn't it? So it doesn't have its axis, does not spin around its axis. When you write the Hamiltonian, you assume there's an electron nucleus, then because this coordinate system you need to write down the Hamiltonian. But the electron is actually, this wave particle duality. So as a result, electron is not an object which is spinning on its axis. So people use those things and explain things. These are wrong. I'm telling you. Anish, you know this, no? I'm not sure, Anish. Yes. But this is not stressed in chemistry courses, no? That electron spin has nothing to do with physical spin. But this is very, very important.
So it's some intrinsic property of any system without any classical analog.
There is no classical analog. It is some degree of freedom of your electron, of any subatomic particle, but it has no classical analog. Yes, that is how it is. So not everything you can understand using classical mechanics, using your. So there are many things, like most of the things in quantum mechanics has things in quantum mechanics, they have no classical analog. Okay.
so does nuclear spin like same thing applies to nucleus?
Same. There is no such spinning in nucleus.
Yeah, like this is like deeply explained in NMR spectroscopy, like it's spinning this anti-clockwise and clockwise.
Yeah, all these things are wrong, but people do. Just I don't know why they do, but people do. Yes. But if you read physics books, you'll never find that. Rarely find that. That is a classical picture, but it is not like that. There's a clockwise, anti-clockwise, all these things are wrong. Yes. So this subatomic particle spin, they have no classical analog. That you get here, huh? Don't forget. Very, very important. Extremely important. Yes, someone has a question?
Sir?
Yes.
I have one question. So that is not related to this. Sir, if we think, sir, if we consider the electron, it has plus half spin, then we consider this, it is spin clockwise direction. If it is minus half, then it is anti-clockwise direction. So this is for electron. But if we consider boson, if we consider for photons, which have the integer spins, that is 0, 1, 2, 3, then sir, how can we actually
No, that's why.
think
That's
of?
why. That's what I'm
Yes, sir,
saying. That
yes,
you should not think in terms of plasma,
Yes,
up electron, down electron, clockwise, anti-clockwise. All these things are wrong. So
yes, sir, yes, sir.
electron has 2 spin states. Okay, but you can have particles which has many spin states. Then what will happen to that? You know. So,
Yes, sir.
so I think it is better not to think about use this language. When you are in school, people use that, but when you cross school, like class 12, you should not have this. Those things sometimes help. Okay, sometimes help in not in understanding, but solving some problems. Maybe when you do hybridization, no, one spin up, one spin down, you couple them, no.
Yes, sir.
You put electron from the other orbital, and you make sp3 hybridization, no. Inorganic chemists, they do that. Not right, but it is there. Chalta hai type. Anyways, so but it is a physical chemistry course, so you have to know all these things. If anyone asks you what is spin, you say there is an intrinsic property of electron or any subatomic particle. It has no classical analog. That is most important. Most important. Okay. So we'll wrap up. If someone has a question, we can wrap up today a little early, and we'll meet day after tomorrow. Okay, one more thing. Can I have a meeting? Can I have a class on Saturday rather than on Thursday? Saturday, do you have a class? Maybe Saturday also have a problem. Let's see. I'll let you know. I'll let you know. Anyway, anyone has a any question? Any queries?
Sir, what will be your evaluation pattern?
That is more important. I think learning is more important than evaluation pattern. Okay. So I plan to have one. I'll give you some at least two sets of assignments, and then we'll have end-sem exam. That is how it is. I plan.
Okay, sir.
So how many exams you had before mid-sem?
Just one assignment.
Of quantum?
One assignment.
Assignment and mid-sem.
Okay, I'll give you two set of assignments, two set of problems. Okay?
Okay, sir.
Okay, sir.
So don't worry about those things. And any questions so far? Please go through my video. Go through my video. Yeah, Shupriyo. You are in which course? 425 or 812?
Sir, 425.
Okay, yeah. Tell me.
Sir, in hydrogen atom, when you define the radial distribution function, sir,
Okay.
the volume component that we are taking, sir, is it 4 pi r square dr or it is only pi r square dr?
It is 4 pi r square dr if it is spherical, because 4 pi comes from integrating sine theta d theta d phi. D phi gives you twice pi, sine theta gives you 2. That gives you 4 pi. Okay. So ideally, it should be r square dr. I am telling you, r square dr sine theta d theta d phi. That is the volume element.
Yes, sir. Sir, if we take
tell me.
If we take no angular dependence, then sir, theta part and phi part that should be normalized.
Yeah. So that will go. That will give you 4 pi. That will give you 4 pi.
Okay. Yes, sir. Yes, sir.
For sphericals, for s orbital, isn't it?
Yes, sir. Yes, sir. Yes.
Because it has s orbital has no theta or phi dependence.
Phi dependence. That's
s orbital has what is known as only r dependence, so radial dependence. So that's why you have the 4 pi factor coming. Twice pi comes from phi, from 0 to twice pi, and sine theta d theta, if you integrate from 0 to pi, it gives you 2. 2 into twice pi is 4 pi. Is this clear?
clear, sir. Clear.
Yes. Anyone else? Okay, I think we'll meet day after tomorrow. Hopefully, if I change my mind, I'll let you know. Hopefully, we'll have class day after tomorrow. So I'm going to now.
Sir,
Yes.